You pick up a freshly machined steel block. To the naked eye, and even to the touch, it feels perfectly smooth. But that smoothness is an illusion. At the microscopic level, two metal surfaces sliding against each other don't glide. They are jagged, mountainous landscapes, violently colliding and tearing at one another. The engineering study and precise quantification of these microscopic peaks and valleys on a solid object is known as surface finish. Before a single cut is made in the shop, engineers mandate these surface tolerances using specific blueprint symbols: a basic checkmark, a checkmark with a horizontal line, and a checkmark with a circle. These symbols define strict mathematical parameters. They dictate exactly how much friction a part generates, how quickly it wears, and how it fits into a final assembly. Surface finish is a structural necessity. The exact topography of a part determines the functional lifespan of every modern mechanical system. To control this microscopic landscape, engineers deconstruct surface texture into three distinct, measurable layers. The first layer is roughness. These are the primary, high-frequency spikes and craters carved directly into the metal by the machining tool. Underneath that roughness lies the second layer, waviness. These wider, low-frequency waves act as a rolling foundation for the jagged spikes. While roughness comes from the cutting blade itself, waviness is a physical record of the machine's flaws, specifically unwanted machine vibrations or tool deflection during the manufacturing process. The third layer is lay. When we look at this surface in 3 dimensions, we see that the cutting tool leaves a dominant directional pattern or grain across the material. Depending on the specific equipment used, this grain can be laid out in a parallel grain, a circular pattern, a radial layout, or even cross-hatched configurations. By mapping the roughness, the waviness, and the lay, engineers isolate the physical anatomy of the surface. Only then can they apply mathematical metrics to measure it. Engineering relies on exact numbers. The physical topography we just mapped must be converted into standardized metrology. To measure a rough surface, we first draw a theoretical mean line straight through the center, bisecting the peaks and valleys. From here, we calculate RA, or arithmetic average roughness, by averaging the absolute values of all deviations above and below this line. RA is the standard baseline across manufacturing, but relying solely on an average creates a mathematical blind spot because averaging naturally hides extreme anomalies. To catch those anomalies, engineers use the RZ parameter. This isolates and measures only the vertical distance between the absolute highest peak and the deepest valley within the sample area. For absolute clearance limits, the RT parameter measures the total maximum height from the highest peak to the lowest valley across the entire profile length. A single microscopic spike won't significantly change the RA average, but it can trigger a catastrophic part failure under pressure. High-performance engineering requires multiple parameters to reveal the true condition of the metal. Calculating these mathematical parameters is only half the equation. The shop floor has to physically generate them. The first variable is cutting speed. Rotating a part at higher speeds against a tool generally slices the metal cleaner, yielding a finer, smoother finish. Next is feed rate, the speed the tool physically advances along the material. Moving slowly creates tight, closely overlapping ridges. Increasing that feed rate leaves wider, more aggressive gouges in the metal, severely degrading the final RA value. Even with perfect speeds and feeds, dull tooling or slight machine vibrations introduce chaotic forces that can instantly ruin the final topography. The baseline material dictates the outcome as well. Softer metals are highly forgiving and relatively easy to slice smoothly, whereas hardened alloys resist the blade and complicate the finish. Hitting a precise mathematical surface parameter demands strict, inflexible adherence to the physical laws of machining. Manufacturers rely on a hierarchy of distinct processes to hit different tiers of surface quality: rough, smooth, and super finished. Rough outcomes come from processes like casting and forging. They are cheap to produce and offer strong grip, but they generate massive amounts of friction. Moderate, smooth finishes are achieved through turning on a lathe or milling. These cut the metal directly and leave clear, geometric lay patterns on the surface. Extreme environments, like aerospace bearings and high-stress engine internals, require the super finishing tier. To drop the RA value drastically, engineers switch to grinding. This abandons single-point cutting blades entirely, using high-speed abrasive wheels to shear away microscopic amounts of material. For internal geometries, a process called honing is used to scrub the interior walls of automobile engine cylinders to an exact tolerance. At the very top of subtractive metrology is lapping. This is reserved for parts that require absolute flatness and the absolute lowest possible roughness. When precision demands hit the micron level, traditional blades fail. Engineers must switch entirely to controlled microabrasion. A superfinished surface is useless if you cannot verify its exact dimensions. Old methods, like visual inspection or running a fingernail across the metal, lack the accuracy needed for modern industry. The primary instrument for modern verification is the surface roughness tester, commonly called a profilometer. This diagram shows the stylus method in action. A microscopic diamond-tipped needle physically drags across the machined surface, tracking every peak and valley. The vertical displacement of that diamond stylus is electronically converted into the 2D graphs and precise RA calculations we analyzed earlier. The stylus method requires physical contact. If you drag a diamond across fragile nanoscale components like microchips, you destroy them. For highly sensitive parts, engineers use non-contact optical methods. Interferometry measures the topography by analyzing the interference patterns of light waves bouncing off the material. At the extreme end of the scale, atomic force microscopy measures surface variations down to the atomic level. Without precision metrology instruments to verify the data and close the loop, manufacturing high-end components becomes blind guesswork. If superfinishing creates the least friction, why don't engineers just polish every single moving part to a mirror finish? A perfectly smooth surface actually creates a critical point of failure. It cannot retain oil. Without a place for lubricant to grip, rapidly moving metal parts will grind dry and seize under extreme heat. Look at this moderately rough surface. Components like engine cylinders require deliberately engineered roughness so deep micromallees trap and hold microscopic pools of oil. Conversely, roller bearings require the lowest possible RA to minimize dry friction and ensure effortless movement. Beyond physics, there is an economic reality. The cost curve of surface finishing is exponential, not linear. Taking a part from a standard machined finish to a superfinished, lapped state drastically multiplies the manufacturing time, the energy required, and the final cost. Perfect engineering requires hitting the specific roughness target mandated by a part's environment, balancing physical survival against economic reality. The process follows a strict loop, reading the exact drawing symbol, setting the precise CNC machine parameters to achieve it, and verifying the final RA with a highly sensitive profilometer. This exact sequence of translation and verification prevents catastrophic failures in systems where humanity simply cannot afford mistakes. Inside an aerospace turbine spinning at maximum velocity, a single micron of unwanted surface deviation can generate enough stress to tear a titanium blade apart. The metrology manufacturing loop acts as a permanent dialogue between abstract mathematical standards and the brutal physical realities of friction. Surface finish is the invisible architecture of the modern world. It quietly dictates the mechanical boundaries of everything we build.